We're on page 99 here. So the thing that we're interested in for the tree diagrams, one of the things we need is this conditional probability. We were talking about some kind of harder problems last week, but here it'll only come up in the context of a tree diagram. Now I've already just noticed one small error down here. So this is not on the tables, so you get used to it and you kind of, you get used to it, you use it a couple of times and then you remember it, or else you come up with it like this. The probability of A and B would be the probability of A times the probability of B given that A is true. And so to get something like the probability of B given that A is true, you divide both sides by the probability of A. So this shouldn't be B, this should be A. Okay, now there are slightly different formulas, but I mean, all you're going to be doing is putting in events here, the probability of this given that this is true. And the important thing is, so it's this and this divided by the probability of the second one.
The top formula should be A as well, so.
No, the top formula is right, they're different things.
Oh.
So this is probability of A given that B is true, this is probability of B given that A is true.
Okay.
Because you'll just be putting in whatever you want in for A and B. Okay, so jumping ahead to page 101. This is where we were last week. So this tree diagram often comes up in question 1. So we have a starting situation, we have a random phone. We know 25% are Samsung, 35% are Nokia, 40% are iPhone. They should add up to 100, and they do. And then we've got the phones are either defective or good, defective or good, defective or good. And we're told the probability of Samsung is defective, or rather we're told 3% of all of them are defective. So the probability therefore of one of them being defective is 3%. And we've also got 1% and 2%. And if there's a 3% chance it's defective, there's a 97% chance it's good. So that's where you get 99 here and 98 here. So this is your tree diagram. And the idea is you're starting with a random phone and you've got 6 different possibilities. A random phone can be Samsung and bad, Samsung and good. Nokia and bad, Nokia and good. iPhone and bad, iPhone and good. So we've got 3 questions then. Find the probability that a mobile phone chosen at random is a Nokia or an iPhone. Now most of the time or will just mean plus, particularly when, or definitely when the things can't happen at the same time. Can a phone be both Nokia and iPhone? Without getting too smart about it? No. So the or will mean plus. So this is the probability of a Nokia plus, so this U here means or, so U is equivalent to or. Do you ever use this yoke in truth tables? No, that'd be another way of writing or. Okay. So probability of Nokia plus the probability of iPhone. What is the probability that a random phone is Nokia? 0.35. And what's the probability that a random phone is an iPhone? 4. So you get 0.75. So that one is handy. So the or, if they can't happen at the same time, means plus. The and, if they're independent, means multiply. So the next question is find the probability that a mobile phone chosen at random is defective. So the question is, how can you end up with a defective phone? So not talking about numbers, but how could you end up with a defective phone? Well, yeah, but that's all captured in these numbers here. So there's 3 ways that a random phone is defective. Samsung and defective, Nokia and defective, and iPhone and defective. It should say, so there's actually a little, probably a bit of subtlety in the question. It should say that the mobile phone chosen at random was bought in the shop. So there's 3 different ways this can happen. You can either go here, here, or here. It will be in a second, yeah, but to get this, yeah, so here we'll do the add. So this is or, so Nokia and Defective, or iPhone and Defective, or Samsung and Defective. So we can put in the plus here. Now I'm happy enough with you going to the 3rd line, but we'll take the or means plus. So Nokia and Defective. So you can't be Nokia and Defective and iPhone and Defective at the same time. They're mutually exclusive, so the or means plus.
How do you know that they're exclusive to each other?
Well, barring really weird things, can a phone be Nokia and Defective and iPhone and Defective at the same time? No, unless this phone is 2 phones put together, it can't happen. And it'll be the case most of the time from here on in. Now, the ands, now these things aren't quite independent, but what you have is you're going to do the probability of Nokia and or times the probability of Defective given that it is a Nokia. So these ands are going to be multiplied. So these are the same as ands, which mean multiply. So what's the probability of a Nokia?
0.3.
Yeah. Now what's the probability that it's defective given that it's a Nokia? 0.01. Plus, what's the probability of an iPhone? 0.4. Times, what's the probability that it's defective given that it's an iPhone? So here's your probability of iPhone, and given that it's an iPhone, what's the probability of defective? 0.02. Probability of a Samsung? 0.25. And times the probability that it's defective given that it's a Samsung? 0.03. Now I'm quite happy with you going straight from there to there.
You just roll out the same thing basically, didn't you? And the second line?
No, these are different, but they're equal. These two? See, the R's mean plus.
Oh, sorry.
Yeah. Now, in this section, if you have any decimals, I want to see 4 significant figures. If possible, this comes out exactly 0.019. Has anyone can anyone explain in a rough way why that is smaller than 2% rather than bigger than 2%?
It's not 0.02 like.
It's close.
Are we just like?
It's a bit smaller. Why
are we
is it?
saying 0.02 is 2%?
Oh, it is, yeah.
Yeah. So why is it like? Is it?
Yeah. Why isn't it bigger than 2%?
Is there?
There's a reasoning.
Is there?
There is a reasoning. Yeah.
All good phones.
All good phones, right? What are the good phones? So it's less than 2%. What are the phones that are 2%? Where am I getting 2% from?
iPhone.
The iPhones. So if they're all iPhones, the answer would have been 2%. Right, but they're not.
Is it because you're accounting for all 3 phones?
You're accounting for all 3 phones, but why isn't it bigger than 2%?
Because the majority of phones are which are
phones.
Nokia.
Or rather,
Sorry.
if you forget the iPhones, yeah?
Go for Nokia.
Yeah, most of them. So forget them. Most of the other ones are less than 2%. So they'll count more. And that's why you get an answer less than 2%. Okay, so basically the situation is, say iPhone is the standard, that should be 2%. But there's more Nokias out there than Samsungs, and the Nokias are better than the Samsungs, so that's why the number is less than 2%. There's more better phones than crap phones. So you'd say this is kind of the average phone, not in a sense of mean, just kind of it's the middle phone. These are the good ones, these are the bad ones, and there's more good than bad, which makes that closer to 1% rather than 3%. Okay. Last question. A certain mobile is found to be defective in the CIT shop. Find the probability that this defective mobile is a Nokia. So if we come up here, what you have is it's found to be defective, so this is true. So you're looking for the probability that a phone is Nokia, given that it is defective, that's true. So that means a conditional probability. So you've got extra information, how does the probability change? And that you use, so it'll be the probability of a Nokia given that the phone is defective. And using the formula on the previous page, so when you got probability of A, given that B is true, it is the probability of A and B, in this case N and defective, divided by the probability of defective. Now, we'll get a rough idea of the numbers here. So see, can we kind of predict what the answer is going to be?
That formula is in the table, is it?
No. So, is a Nokia a good phone?
Yeah.
Yeah, so it's kind of unlikely that a defective one will be Nokia. So you should expect this as small. And the amount of Nokias is kind of normal. You know, it's pretty average. They're mostly iPhones and less of them are Samsungs. So there's not much going on here, but there's a lot going on here. So this number should be quite unlikely because your Nokias are good. It would be most likely definitely that, well, it's hard to say pick between Samsung and an iPhone. iPhone because there's loads of iPhones, Samsung because they're crap here. So this probability should be quite small. I can't put any number on it until I calculate it. It's very hard to get a feeling for this. So probability of Nokia and defective. So what's the probability of Nokia? 0.35. And given that you have a Nokia, what is the probability that it is defective? 0.01. Divided by probability of defective. Do we know that? 0.01. No.
No, it's going to be the total.
Total defective. That any phone is defective. Do we have that?
0.3 like.
So
0.019.
yes. So this is the probability that a phone is Nokia, given that it's defective. So the probability of a phone being Nokia and defective divided by the probability that the phone is defective.
Overall,
Yeah.
0.06.
0.0. No.
0.19, yeah.
0.01. That's the probability of a defective phone. And I expect this to be on the small side. I don't really know what small means though. So it comes out to 4 significant figures. 0.1842. Now I'm claiming that is small. Why would you say that's small?
Just
Because
it's just the percentage of Nokia.
Say no. Well, what is the percentage of Nokia phones? 35, and it's way lower. So if all the phones were the same in quality, if a phone is defective, it would be equal chance of each. But because the Nokias are better, it's far less than 30. It's about half. Okay. But these numbers, like to come up with these in an intuitive way, is very, very difficult. Okay. So there are your 3 diagrams. You will be wanting to work on them. They'll be in question 1. Okay. The other thing you're going to be interested in, because in question 1 is the compulsory, is this next section, page 103, reliability block diagrams.
It's a compulsory question, you say.
Now it's not guaranteed, but it's a good bet, yeah. So another question here. So many systems, so if you talk about different systems, you're interested in their reliability. So examples of the kind of thing we're talking about, driving a car, you need the first wheel and the second wheel and the third wheel and the fourth wheel. Driving a truck, am I correct? If you have a big enough truck, they can lose some wheels, can they? Can they? And drive on?
Yeah.
They can punctures and drive on, yeah. So 18 wheels, maybe they can lose 1 or 2 particular ones. So you'll have to have, say, maybe you'll need 14 of the wheels maybe, and this one, or both, and this one or both, something like this. Another one would be something like a torch. For example, there you need the battery, the switch, and the bulb all to be working. If one of them goes, it doesn't work. They're all kind of more, well, apart from the truck, they're called series systems. You need everything working in it. So another one, so basically where there's no double checking. Now something where, a kind of a different thing, a parallel system is like when you have a co-pilot. One pilot can die and you can still fly the plane. What's the problem? If both pilots die, then you're in trouble. Another example of that would be maybe you've got in a kind of controlled measurement situation, maybe there's a gas or something like that, and it has a digital check, but there's also a visual check as well. Maybe the color changes. So that would be a parallel system. If the digital thing messes up, you still have someone actually checking it as a backup. Or if you don't check it, you have the digital. That would be parallel. So these kind of questions. So we'll look at some examples of it. So the first is a torch consisting of a battery, switch, and a bulb assembled in series. Now I don't mean series in the sense of resistors and stuff. I mean that all of them have to work. So if you're looking at this, it looks something like this. So first of all, maybe, and actually there's probably a natural order, but actually it won't really matter. I mean, say, oh, I need the battery to work, I need the switch to work, I need the bulb to work, but you could put bulb first, it doesn't really matter. We'll run with battery. So this has to work. We'll say the switch has to work, and we'll say the bulb has to work. Now the numbers we give are probably a little bit difficult to interpret. May I suggest that those numbers are the probability that they work for a year, 6 months or whatever, something like that. If they were new torches, the numbers would probably be bigger, and they'd be the probability that they weren't defective. But probably a reasonable way of thinking about it is maybe 0.9 is the probability that the battery lasts, let's say, 6 months, all else being equal. So that would be what that 0.9 represents. Say the switch, say there's a 0.8 probability that the switch works for a year, and there is a 0.7 probability that the bulb works for a year, or maybe let's say works for 24 hours continuous use, something like that. Now, what we're interested in is, now the product, so T be the event that the torch system is reliable, let's say for argument's sake for 24 hours, and what we're interested in, what is the probability of the torch working for 24 hours, something like this. So what you will need for the torch to be reliable for 24 hours, you will need the battery working for 24 hours, and the switch working for 24 hours, and the bulb working for 24 hours. Now we can go into little dark holes if we want here and say stuff like, you know far more about electronics than I do. Maybe when the battery goes a bit dodgy, something bad can happen with the bulb. If that was the case, what I'm going to do next doesn't really work. But we'll assume that they're independent. So how this works and how this works and how this works. In other words, if this goes, it doesn't make it any more likely that these go on their own. Okay. So the AND would mean multiply. So you got the probability of the battery. What's the probability that the battery works for say 24 hours? 9. And means multiply, and the switch working for say 24 hours. And the bulb working for say 24 hours. 0.7. And then just multiply these together. 0.504. So, I mean, to make sense of the numbers, we have to give it a bit more. I mean, for me, I'm probably saying they're crappy numbers. I mean, I don't know how long a torch would last. Would it last for 48 hours? The battery lasting 48 hours is 0.9, fair enough. The switch, that should probably be way higher, and maybe that one's fair enough. So it's these kind of calculations. So this is an AND system, a series system. The other one would be a parallel system, or it'd be an OR system. So yeah. So this a parallel will be one if it fails only if everything fails. So an example is 2 pilots on a 2-person craft, for example. So it works as long as they both don't. If they both die, you're in trouble. So we'll look at it something like this. This is how I'll draw it. Pilot 1, pilot 2. Now again, we get into, if we go too deep into it, you get into problems with independence. So if one pilot dies, it actually makes it more likely that the other one dies as well. Because if you think about what the first person died of, maybe they both had the same food or something. So they're probably not independent.